Welcome to the second part of our lead-acid lecture, where we were to look on the operation of those lead-acid batteries. And to do so, let's have a look on the basic equivalent circuit of a lead-acid battery. And we can explain that it's just a serial connection of a direct voltage source with a resistance for the inner resistance. And there we can connect the loads. The inner resistance is not a constant, it varies something between 6 and 9 milliohm and depends on the temperature and also on the state of charge or state of discharge. But we cannot explain everything by this very basic equivalent circuit. So for example, that shows the measurement of the discharge of a lead-acid battery with a constant current that we can see on the yellow bar. And then we see the development of the voltage, that on the long term it's a slight decrease in the voltage, but in the very beginning on the left side we see an immediate decrease of voltage. And then in the end, when we stop discharging, we see that the voltage again is recovering a bit and is increasing. And that cannot be explained with the basic circuit. The reason for that is mainly that the acid concentration is different in the container and in between the pores of the positive and the negative plate. And that is a reaction or a function of the diffusion process. When we discharge the battery, we have the diffusion of new H2SO4 members towards the pores, and that is different when we discharge them faster or slower. That means when we stop discharging the battery, we still have a diffusion current going towards the pores, resulting that the voltage is increasing again. And that we can explain in a quasi-static equivalent circuit of the lead-acid battery when we add here a capacitor or the parallel connection of a capacitor with a resistance. We can also add other phenomena of lead-acid batteries. For example, when we charge a battery with a too high voltage, we have a gassing reaction. That means that the water is spread into hydrogen and oxygen. And that we can symbolize here by this Zener diode in series with a resistance. That means only when the voltage is higher than a certain limit, 2.4 volt per cell for example, then we have here this short circuit through the Zener diode symbolizing this side reaction. And then we also have this RS, another resistance in parallel, quite big resistance in that circuit, but that shows the self-discharge. For example, even when we don't have a load connected, we have a self-discharge of the battery. When we see the characteristic discharging a lead-acid battery over time, we see that there are different voltage drops. So we have the horizontal line. That would be the voltage without participation of the electrolyte. But then we have the voltage with decrease of the electrolyte concentration when the battery is discharged. We see it inclusive the resistance of the collector, the resistance of the electrolyte, and the overvoltage that is necessary in order to start the discharge of the battery. And then we get this very typical discharge curve of a lead-acid battery. That, for example, is a characteristic curve of a lead-acid battery delivered by a manufacturer. And there we see with different discharge currents, these are the different blue lines in the diagram, all at 20 degrees Celsius. Then we see the I20 on is the highest blue curve, is discharged in 20 hours, and then we have 2 times I20, 4 times, 10 times, 20 times and 40 times I20. And they all have end of discharge voltage indicated by the manufacturer, and there we already see that the capacity of a battery is not a constant. When we go from I20, where it's 20 hours, then we could assume when we go 10 times I20 it's 2 hours, but we see when we go 10 times I20 it's less than 1.5 hours, so the capacity is not a constant value. On that diagram we see what happens with the capacity when we discharge the battery with different currents. On the horizontal we have the current, the discharge current in ampere, and on the vertical we have the capacity in ampere hour, and when we divide the capacity by current we get time, and that is the straight lines in the diagram with different time perspectives, 1 hour, 3 hour, 5 hour, or even only a few minutes. And there we can see when we, for example, have a low current discharging the battery in 10 hours, we have a capacity of 190 ampere hours. When we do that with a higher current only in 3 hours, the capacity is only 140 amp hours. And when we do that in only 30 minutes, the capacity decreases even to 70 ampere hours. So it's highly flexible. So the battery capacity again is given in ampere hour. The energy that we can discharge from the battery is calculated by multiplying the capacity with the rated voltage. The capacity is not a constant value, it differs with the discharge current, and for example the C20 is the capacity of the battery when it is discharged with a current that discharges the battery completely within 20 hours. And this current is then called the I20. And as a consequence, the C100 is larger than the C20. When we charge the battery, we have all those voltage drops, but on the different side. And what we see, the voltage drops cause that we need a voltage for charging that is bigger than for the system voltage of the battery. The charging factor due to side reactions, therefore, is the rule for charging that the Q charge is bigger than the Q discharge. That results in an efficiency that is less than 100%. And charging velocity is determined by the dissolution of lead sulfate and lead 2+ transportation. And that means just by giving a higher voltage to the battery will not definitely result in a faster charging. It will finally, what can be seen on the highest horizontal line, the gassing voltage, that we have more side reaction instead of a faster charging. So, and when we have gassing, then we lose water, and that means we regularly in a lead acid battery we need to refill water. Also the temperature has an impact while charging. So high temperature accelerates the chemical reactions. Dissolution of lead sulfate and lead 2+ diffusion, and temperature compensation is typically that the required charging voltage decreases by approximately 4 millivolt per degree Celsius with a rising temperature. When we operate batteries, lead acid batteries, their lifetime can be very different and has a lot to do on how we treat them. So the battery life depends on the time definitely that it is operated, and the storage means the lower the temperature and the more often we have a state of charge of 100%, the better is the lifetime. The mean state of charge plays a role. That means we should not leave the battery in a low state of charge over a longer time. The depth of discharge plays a role. That means the depth of discharge is recommended not to be much more or much lower than 50%. Temperature distribution plays a role. It is recommended to be around 20 degrees Celsius. and the same temperature for all the cells, else they behave in a different way. With higher temperatures, always also the side reactions are increased, and therefore also the aging is going faster. Performance requirements: the current level as low as possible, the discharge currents, the longer the lifetime will be, and the charging procedure plays a role. So especially in sealed batteries, overcharging needs to be prevented, else it could be destroyed. In flooded batteries, it's just that the oxygen and hydrogen is released. And the electrolyte level plays a role, so we need to check the electrolyte level. When it's too low and the plates are exposed to air, then we have a corrosion. So to sum that up, sulfating of positive and negative electrode is an aging mechanism. Water loss by too high charging currents is an aging problem. So-called dendrites growth is a problem that could, when they are getting too big, could cause a short circuit. Dropping of active material, that means when those dendrites are falling down into the sludge chamber, that could be a problem causing a short circuit. So ending up with a few questions that can be answered either by the presentation or even by more detailed information given in the script or in the book. What is the difference between a flooded and a sealed lead-acid battery? How are the three types of electrodes called that are used for lead-acid batteries? Describe the advantages and disadvantages of a lead-acid battery. At the negative electrode, why is the hydrogen generation in consequence of a side reaction? How does the grid corrosion affect the lead-acid battery? Name at least 3 applications of lead-acid batteries. How does the temperature influence the charging and discharging characteristic of a lead-acid battery? Name at least 2 aging mechanisms of lead-acid batteries. Why do even sealed acid batteries require a valve? Thank you very much and see you next lesson. Bye bye.